Hello students, in this lecture we will generate a subgroup by subset of a group. First we'll define what that generated subgroup is. A subgroup H of a group G is said to be generated by a non-empty subset S of G if either H is the smallest subgroup of G containing S, or if this set is number one, if the set is a subset of H, and second is if H1 is known is any subgroup of G containing S, then H must be a subset of H1. Number one is if S is a subset of H, and second is if H1 is any subgroup of G containing S, then H must be contained in S1. Then and only then we see that H1 is a subgroup generated by the non-empty subset S of a group G, right? Or it is noted by, if this subgroup is generated by a non-empty set S, then we say that H is generated by S. Means H is a subgroup generated by S. So, in order to understand all this, let us prove this theorem. If S is a non-empty subset of a group G, then there exists a subgroup of a group G generated by S and is equal to the intersection of all subgroups of G containing S. What is here? If S is a non-empty subset of a group G, then there exists a subgroup of a group G generated by S and is equal to the intersection of all subgroups of G containing S. Proof is, let us assume that F consists of all subgroups of G containing S. That is, suppose the set F is the set of all subgroups of G containing S, that is H, all H which contain S. That's a subgroup which contain S. Since every set is a subset of itself, every set is a subset of itself, therefore G is a subgroup of G and S also is a subset of G. So G is also element of F. G is also belongs to F, means G is also element of F. So this means F is a non-empty set. Is a non-empty set. So let us suppose that K is the intersection of all the subgroups of G containing S. Let K is the intersection of all the subgroups of G containing S. Since the arbitrary, we know that arbitrary intersection of subgroups of G is again a subgroup. We have proved this in the earlier lecture. Any arbitrary intersection of subgroups of a group is again a subgroup of G. Therefore, K is a subgroup of G. It is a subgroup of G. Since S is a subset of H, for all H belongs to F. So, for all H belongs to F, so there, if we find the intersection, because S is a subset of all H belongs to F, so this implies S is a subset of intersection of all the subgroups of this set F containing S, which is equal to K. This implies, therefore, K is the subgroup of G containing S. K also contains S. K also contains S. Now, if H is now suppose any of the set, you take any of the element of F. Now, if H is a subgroup of G containing S, then H also belongs to F. This means and intersection of this means if H is belongs to F, then intersection of all, because all H in this intersection belongs to F, so this intersection of all subgroups of F containing S will be a subset of H. What is this? This is equal to K. K is a subset of H. Implies K is equal to intersection of all subgroups of subgroups H of F containing S is the smallest subgroup of G containing S. Now next question is let G be a group of Q root of field. That is, what are the elements of G? 1 omega omega square. We solved this equation in the previous class in the chapter complex number. Let S consist of a single element omega, and this omega also belongs to G, therefore S is subset of G. Let H is a subgroup of G containing S. Let us suppose H is any, H is a subgroup of G containing S. So this implies S also is subset of H, and H is subset of G. So this implies if S subset of G means H, this omega also belongs to the H. If omega belongs to H and H is subgroup, therefore closure property holds true. Omega into omega, closure property. Omega square also belongs to H because it's subgroup. And omega square to omega, so omega cube. Omega cube is we know that it is equal to 1. The product of cube is equal to 1. So it belongs to H. Therefore, H contains all the elements of G. H contains all the elements of G, so implies G is a subset of H. Then first H is a subset of G, and we prove that G is a subset of H. So first and second implies G is equal to H. So this implies G is also generated by S. G is also generated by S. Complete the proof. Now let's take another question. Show that the order of every element of a finite group is a divisor of the order of the group G. Show that the order of every element of a finite group G is the divisor of the order of element group G. So let us show that G is a finite group. We are given G is a finite group, and let this order is equal to 1. Its order is equal to, this is a finite group. Its order is equal to, and A belongs to G. G B of order M. G B of order M. Order K is equal to, yes, now what to prove here? We have to prove that order of A divides order of G. Means M divides M. So now G is a finite group, so H is also subgroup G. So it must have finite finite number of elements. How many? Order of this. Let's generate the H by these elements. Element A. So A order of A is equal to M. Therefore, A for M is equal to 1. So elements of H are A for N is equal to E. A square is equal to M of 1. A finite subset of G. Now, in order to complete the proof, we will show that H is a subgroup of G by using the lemma, that is, a non-empty finite subset of a group is a subgroup if closure property holds in G. We prove this lemma. What this lemma is? A non-empty finite subset of a group is a subgroup if closure property holds it. And then Lagrange's theorem implies that. So let us take any two elements. Belonging to, which will show closure property here. Any two elements belonging to H, AI and AJ belongs to H, be any two arbitrary elements of H, with the condition that 0 less than equal to I and J less than equal to I less than. And if your I plus J is less than M, so that implies their product is element of H. But if I plus J is greater than M, then we have to apply this division algorithm. If you divide I plus J by M, we must have the quotient and remainder. Q is quotient, R the remainder, such that 0 less than equal to R less than M, the remainder is less than M, and I plus J is written as MQ plus R. So AI, which is what we are checking for. AI into AJ, two elements of H. This will AI plus J based in power add. And this is holds to the group. We have proved it earlier. So we substitute the value of I plus J, AI and Q plus R. Separate them, A and Q is for R. A M is for Q is for R. A is order of A is M, therefore A is for M is equal to E. E is for Q is equal to 1. E is for Q is equal to E, E into A is for R is equal to E is for R. R is less than 0 less than R is than M. If this implies A is for R also belongs to H. Since R 0 is less than R is less than M, 0 less than 2 R is than M, so A is for M belongs to N. Hence, A is for I plus A into A is for J belongs to H. Closure property holds true in a finite set H. Root in it, therefore H is a subgroup of G, subgroup G of order N. And H is a subgroup of G of a finite. H is a subgroup of a finite group G. H is a subgroup of a G of order M. H is a subgroup of G of finite group G. H is a subgroup of finite group G. Therefore, by Lagrange-Miller theorem, order of H must divide order of G. That is, M must divide N. What is M? M is the order of A. This implies order of A divides order of G. This is also proof of the following statement. Let G be a finite group and A belongs to G, then order of A divides G. The same proof. Given if the theorem is asked in this way, or this problem is asked in this way, proof will be the same. Now next question is, if H and K be two subgroups of group G, then show that H intersection right coset of H intersection K is equal to right coset of H intersection right coset of K by A for all belongs to solution for this question. Also can also in another way, let H and K be two subgroups of the group G. Show that any coset relation of H intersection K is the intersection of a coset relation of H with the coset relation of K. The intersection of coset relation of H with the intersection of coset relation of H with the coset relation of whether left or right. So both way we can solve this problem. So both way we can prove it for left coset. Given H and K are two subgroups of a group G, and A belongs to GB and any identity. What to show? We will show that right coset of H intersection K is equal to intersection of right coset of H and K by A. Reason I to in order to prove this, we have to prove H intersection right coset H intersection A by A is a subset of right coset of A, H by A intersection right coset of K by A, and second is right coset of H by A intersection right coset of K by A is subset of H intersection right coset of H intersection. So that's the first part. We take in help the intersection. First part is this: to show that right coset of H intersection K by A is a subset of right coset of HA intersection right coset of K by A. So now this. Since we know that H intersection K is subset of H, you can so you know from the knowledge of the this set theory Venn diagram, and H intersection K is subset. Okay, so when you combine both, we will get that or convert it into right cosets. If this is subset of this, then right coset of H intersection A is a subset of right coset of HA, and right coset of H intersection K by A is equal to is a subset of right coset of K. When you combine both results, you come to the conclusion that right coset of H intersection K is a subset of right coset of H under A intersection right coset of K under A. So now second part is to prove that to show that right coset of HA under A intersection right coset of K under A is a subset of right coset of H intersection K. So let's see from this X belongs to this. belongs to H intersection right to H intersection right to H under H under A intersection right to K under any of them this element. If H belongs to now the definition of intersection. If H belongs to this implies H belongs to HA and H belongs to KA. H belongs to right to H under A and X belongs to right to K under A. So if H belongs to HA means what type of element X will be? X belongs to this, X will be the type H into A, X belongs to H, and if X belongs to KA, this implies X will be type K into A for K for some K. Now H and what are H and K? H and K are subgroups. Therefore, cancellation of holds true. H. So in this equation, apply right cancellation by A inverse in both equations. Distribution and distribution. We got H is equal to X inverse, X into A inverse, and K is equal to X into A. So from these two equations, we can conclude that H is equal to K because right hand side equals, left hand side must be equal. H is equal to K is equal to X inverse. So what this implies? This implies X inverse also belongs to X inverse also belongs to H in section 2. Section in definition goes on. If this belongs to uh, X inverse belongs to H in section K, this implies now let's convert it right process. Therefore, X inverse A belongs to the right coset of H in section K. Okay? Associative the whole student because the section subgroup. So A to associate to the holes. So X inverse A can written as X inverse A is equal to E. So E into X is equal to E into X is equal to X. X belongs to intersection right coset of H intersection. So we suppose X belongs to right coset of H under A intersection right coset of K under A, and we have shown that X belongs to right coset of H intersection K. A and B implies right coset of H intersection A under right coset of H intersection K under A is equal to right coset of H under A intersection right coset of K under A. Now next question is let H consist of 1 and A square be a subgroup of G consisting of these four elements A square, A cube, A square 4 is equal to 1. What to do now? Find all the left cosets of H and G. Show that the union of these cosets is equal to G, and any two cosets are either disjoint or so. We have to show three things. Like taking this example. So H is given. H is two elements A and A square is a subgroup of G, and second is G is given having four elements A square is of Q, A to 4 is equal to 1. Now let's find the left coset H. You can find right also. So multiply by 1 H 1 into H. H will be equal to 1 into 1 is equal to 1 to A. This will equal to H. So 1 into A, again, you can see. Now A into H is equal to multiply the element of H by A. A. Similarly, this is equal to A square into A is equal to A is equal to 4, A square is equal to A square is equal to A is equal to 4 is equal to 1. So 1 to A square. This is again equal to H. And A cube is equal to H is equal to multiply H by A cube. So this is A cube is equal to 5. A cube is a 5 is equal to 4 into A. Is equal to A into A and A is equal to A cube, which is equal to again equal to H. So we can conclude from here that if we find all the left coset of H by the elements of G, we got two distinct two left cosets. Find the left coset to the distinct right cosets of H and the elements of by G of H, you got two distinct right cosets, left coset, sorry. One is H and the other is H. So, and from this we can conclude that H and HA have no distinct elements, so they are disjoint, and the union of H and HA will give us G. They are disjoint, and then substituting